Welcome to today's deep dive where, well, we are looking at a pretty wild technical analysis. It's
Yeah.
about why the future of AI data centers is apparently moving entirely off planet.
Yeah, it sounds like science fiction at first.
Right. I mean, for you listening, Earth's power grids are basically hitting a brick wall trying to power these gigawatt-scale AI clusters.
Yeah.
But space has like 36% more solar irradiance.
And zero cloud cover, plus, absolutely no nighttime.
Exactly. So we are going to unpack this. Just imagine taking ChatGPT and, well, plugging it directly into the sun.
Because we are hitting a hard thermodynamic limit down here. I mean, we simply don't have the clean energy infrastructure to keep up with generative AI's growth.
Right.
So going off planet is, it's becoming a mathematical necessity.
Wait, so if there is endless solar power up there, why not just, harvest it and beam it down?
I know, that sounds easier than strapping fragile server racks to a rocket.
Yeah, exactly. Well, why deal with the launch?
Well, it comes down to physics and conversion losses. You run into these strict diffraction limits with microwaves. Like, if you try to beam raw power from geosynchronous orbit, the beam naturally spreads out.
Oh, because of the massive distance.
Right. A 1 kilometer transmitter in space becomes like a 10-kilometer wide footprint by the time it hits Earth.
A 10-kilometer catcher's mitt just for electricity.
Yeah, a multi-billion-dollar ground antenna. The conversion losses just make it completely unworkable. But if you launch the GPUs up to the solar panels, you can process the data locally.
And just beam the digital results down instead.
Exactly. Transmitting that processed data takes a fraction of a watt. Doing localized AI inference in orbit cuts your downlink bandwidth needs by like 99%.
Wow, okay.
And once heavy lift rockets push launch costs down to around $200 a kilogram, well, orbital data centers actually become cheaper than building on our congested grids.
Okay, so the math actually favors sending the servers up, but space is, a highly radioactive vacuum. You can't just unbox a standard server and expect it to survive.
No, definitely not. Standard silicon solar cells get destroyed by that constant radiation. You need highly specialized materials, specifically 3V semiconductor cells.
Okay, the 3V cells.
Yeah, a company called 5N Plus dominates this market with their Azure space cells. They hit 32% efficiency because their chemistry is, well, it's engineered to resist that degradation.
Right.
But generating the power is only half the battle. You also have to deal with the heat.
Hold on, space is near absolute zero, isn't it? Why are we worried about cooling? Like, shouldn't a GPU just freeze instantly out there?
It would if there were air.
Oh, right.
Yeah, without air, there is zero conduction or convection to pull heat away from the chips. You have to rely entirely on radiating infrared heat into the vacuum.
So it's like trying to cool a high-end gaming PC locked inside a giant vacuum thermos. The heat literally has nowhere to go.
That is a great analogy. To cool a standard 100-kilowatt server rack, you need over 120 square meters of radiators facing deep space.
That is massive. How do you even fit that on a satellite?
Well, that's where new infrastructure comes in. Redwire is building these lightweight rollout composite booms to hold those cooling surfaces.
Okay.
And then Archimea is solving the chip cooling problem with zero-power loop heat pipes.
Zero power. How does that work?
Well, think of how a paper towel, naturally soaks up water.
Capillary action.
Exactly. They use that exact physical force to passively pull liquid coolant across the hot chips. It moves kilowatts of heat without any moving parts that could fail.
So we have rollout booms and passive capillary coolers. But are any of the big tech players actually willing to risk flying their $30,000 GPUs yet?
Oh, it is already happening.
Yeah.
A startup called StarCloud recently launched a refrigerator-sized payload, and, well, they successfully ran a large language model on an Nvidia H100 in orbit.
Wait, really? An H100 is already up there?
Yep. At the same time, Blue Origin is launching their Blue Ring platform, which is built to host massive 4,000-kilogram payloads. It basically acts as a plug-and-play power and propulsion hub for these orbital GPUs.
Wow. So if Nvidia hardware is already running in orbit, they must be getting a massive head start on understanding how their chips handle all that radiation stress.
They are securing crucial early telemetry, yeah. But strategically, they are locking down the ecosystem. By getting space startups to build software on NVIDIA's platform now, they create a space CUDA lock-in.
Right, because developers write code specifically optimized for NVIDIA's architecture.
Exactly, making it incredibly expensive and complicated to switch to a competitor's hardware later on.
So for you listening, when you hear about AI bottlenecks, you really have to start looking past the terrestrial grid. The next generation of compute infrastructure is being quietly built right above our heads.
And it's worth noting, these highly defensible orbital clusters are going to be incredibly attractive for sovereign defense networks. We're looking at placing our most critical infrastructure off-grid entirely.
Which is a pretty wild thought to end on. Because if our most powerful AI supercomputers physically exist in the vacuum of space, far outside any national borders.
Who regulates them?
Yeah, exactly. Who exactly has the jurisdiction? A supercomputer plugged directly into the sun, governed by nobody. Just something for you to mull over next time you're looking up at the night sky.